Gases are not confined by a container that they're placed in, and they don't have a specific shape. So that gases have neither a definite shape nor a definite volume. It is possible for us to confine a gas in some sort of environment, like, say, a balloon, and monitor changes in its volume. It's also possible for us to measure the pressure that a gas exerts. So two key measurement properties we have for a gas are pressure and volume. We've already dealt lots with volume measurements this semester, but not very much with pressure. The pressure that a gas exerts is the amount of force that that gas applies over some surface area. Typically and traditionally, pressure has been measured as a relative quantity, comparing the displacement of a liquid like mercury to some benchmark pressure, say the normal pressure that all the gases in the atmosphere together exert. This means of measuring pressure is a relative means, meaning that we can only know what the pressure of a gas is relative to something else. Therefore, it's useful if we can set some benchmark that we can gauge other pressures by. That benchmark is standard atmospheric pressure, the normal pressure of the gases in the atmosphere under typical conditions. This standard pressure is referred to as 1 atmosphere, with the unit atmosphere abbreviated ATM. Aside from atmospheres, there are lots of other ways to measure pressure. This isn't an exhaustive list, but a snapshot of some of the most common means of units of pressure measurements. We have pascals or kilopascals, millimeters of mercury, or torr, which for all intents and purposes are the same, bar and millibar, psi, pounds per square inch. All of these things can be related back to the atmosphere. And therefore, each one of these identities gives us a conversion factor to move from one quantity of pressure measurement into another. In this chapter, we will primarily concern ourselves with atmospheres when we're doing calculations. So, as an example of how we might convert one pressure unit to atmospheres, let's convert 291.4 torr into an equivalent pressure in atmospheres. This will proceed just like all of the other unit conversions we've done all semester long. We're given a value of a pressure in units of torr and asked to convert that to units of atmospheres, ATM. That means we'll need to get rid of torr and convert into target units of atmospheres. The table up above tells us what the conversion factor ought to be that relates torr and atmosphere. Here, we're told that 1 atmosphere is equal to 760 torr. To convert torr to atmosphere, we just divide by 760. In keeping 4 significant digits, as this is an exact quantity, we'll end up with 0.3834 atmospheres. So, there are many different ways to measure pressure, and as a benchmark to bring all of these pressure measures together, we will use primarily atmospheres as we move through the rest of our discussion in Chapter 9. But keep in mind that we may see any and all of these alternative pressure measures appear. What's going to be universally true is that we will concern ourselves with the characteristics of gases that include measurements of pressure and volume. In addition, other characteristics or measured values that can be relevant to gases are temperature and number of moles of gas particles. So we'll also explore those concepts. we'll give each one of these measured quantities its own abbreviation or symbol: pressure, capital P; volume, capital V; temperature, capital T; and number of moles, lowercase n. As we move through the next slides, we'll explore each of these quantities and the relationships to the others. These relationships are defined by a series of experiments that show a relationship between two of those measured quantities at a time. These relationships are thus named for the experimentalists who identified them. Boyle's law shows us the relationship between pressure and volume. Charles' law, the relationship between volume and temperature. Avogadro's, the relation between volume and number of moles. And Amundsen's law, the relationship between pressure and temperature. The first of these, Boyle's law, shows us that when temperature and the quantity or number of moles of gas particles are fixed, that any increase in pressure on a gas decreases that pressure's volume, and vice versa. So that as pressure goes up, volume goes down for a gas, which makes intuitive sense. If we applied pressure to a gas, if we compress a gas, we expect it to decrease in volume. As pressure goes up, volume goes down. Graphically, if we plotted the pressure of a gas versus the volume of a gas, we would expect an inverse relationship. So that at high pressure, up here along the y-axis, volume is small along the x-axis. At low pressure, down here along the y-axis, volume is large over here along the x-axis. These two things vary inversely, but at the same rate in their inverse direction, so that as pressure goes up, volume goes down by a concomitant amount, by some constant value divided by volume. This relationship between pressure and volume is Boyle's law. Another way to state Boyle's law is to multiply both sides of this equation by volume. And what we end up with is that pressure times volume is always constant for a gas at a constant temperature and with a constant number of particles, or moles. That means that at one set of conditions, the pressure times the volume for a gas must be equivalent to the pressure times the volume at another set of conditions. So yet one more way to write this same relationship is that pressure at one set of conditions times volume at one set of conditions is equal to pressure at a second set of conditions times volume at a second set of conditions. And this is the most familiar means by which to write Boyle's law. Here, P1 and V1 are pressure and volume of a gas under one set. P2 and V2 are the pressure and volume of the same gas under a second set of conditions. This is the first equation in a series of gas laws that will develop over the course of this chapter. So I'm going to keep P1, V1 equals P2, V2 available for the rest of this chapter for us to refer back to. Let's do a few examples of how we can use this equation. Firstly, up above, suppose that we place some helium gas in a balloon whose volume is 44.8 liters with a pressure of 0.5 atmospheres. We'd like to know what the new pressure of this balloon will be if we compress that volume down to 22.4 liters. So we're going to make this balloon smaller. As we make the volume of the balloon smaller, we should expect that the pressure exerted by gases in that balloon will increase due to Boyle's law. So let's apply our new equation that I've moved up here. We know that under an original set of conditions, the original pressure of the helium, P1, in this balloon was 0.5 atmospheres. And the original volume, V1, was 44.8 liters. A good means by which to solve gas law problems for this chapter is to come up with a list of all of the things that we know and try to assign them variables that match the equations that we develop. If we can do that, then picking and plugging into the correct equation is going to be easy. We know further in this problem that our volume has changed. We know a new volume, or a volume at a second set of conditions, V2. What we'd like to know something about is a new pressure, P2. Given these quantities, it looks like the only equation that we have available right now is the most applicable equation to solve this problem. Boyle's law, P1 V1 equals P2 V2. We've got a P1, 0.5 atmospheres. We've got a V1, 44.8 liters. We've got a P2 that's unknown, and a V2 of 22.4 liters. We can divide both sides by 22.4 liters to solve for P2. When we do, liters cancel out on the left-hand side, and we'll just be left with atmospheres. 44.8 divided by 22.4 is 2 times 0.5, keeping 3 significant digits, is 1.00 atmospheres. Our new pressure, 1 atmosphere, is higher than our original pressure, just like we'd anticipated through intuitive analysis of this problem. So, I'd encourage you to pause this video here and try the second problem, then come back for the solution. In the second example, we would like to know a new volume. When a gas that's held in a 5-liter balloon initially at 1 atmosphere has the pressure changed to 0.830 atmospheres. Here, pressure is decreasing, so we should anticipate that the volume will increase. Again, if we make a list of all the things that we know about, we know that at an original set of conditions, the pressure was 1 atmosphere, and the volume of our gas was 5 liters. At a new set of conditions, the new pressure is 0.83 atmospheres, but we're after a new volume. So once more, Boyle's law, P1 V1 equals P2 V2, seems like the appropriate choice for solving this problem. P1 times V1 equals P2 times V2. This time we'll divide by 0.83 atmospheres on both sides. We should keep 3 significant digits once again. Our units of atmospheres cancel out. And we should come up with a new volume of 6.02 liters. This volume is larger than the original volume of 5 liters that the gas in this balloon occupied. Just like we'd anticipated, our volume has increased as our pressure decreased. Our second gas law, Charles' law, shows us the relationship between volume and temperature. At a fixed pressure and a fixed number of moles of gas, The volume of a gas varies directly with increasing temperature, meaning that as temperature increases, the volume of a gas increases, or as a gas gets hotter, it expands, which again seems to make intuitive sense. Here, we can say that as temperature goes up, volume goes up for a gas. And in the same way that we described Boyle's law, we can also describe Charles' law. A plot of volume of gas versus temperature, like shown above, will be a straight line moving upward. The only caveat to this relationship is that the temperature at which we measure our gas must be in units of Kelvin, the SI unit of temperature. The Kelvin temperature is equal to an equivalent temperature in degrees Celsius plus 273.15. But for most good approximations, we can just concern ourselves with the plus 273. We need an absolute temperature or Kelvin temperature in order to make the math of this work properly. Because in Charles' law, the relationship between volume and temperature is direct. It's a straight line. And a straight line has an equation that looks like this. The volume on the y-axis is equal to the slope of a straight line, which is a constant value multiplied by whatever's on the x-axis, the temperature. Here, the intercept is 0, which reflects the absolute zero temperature. It is possible to have a zero temperature that's not the coldest possible temperature in the universe on a Celsius scale and also on a Fahrenheit scale. And it's possible to have negative values of temperature on Celsius and Fahrenheit scales. But the Kelvin scale is an absolute scale, meaning it starts at 0 and works its way up. Therefore, there can be no negative numbers, and 0 is only a hypothetical value on the Kelvin scale. That allows the math of this equation to work properly, because what we're going to do with this equation is divide both sides by temperature. We're going to say that for a gas at constant pressure and constant number of moles, the volume of that gas divided by the temperature for that gas is constant. We need the value in this denominator to never be 0. Otherwise, we blow up the universe. Therefore, we choose a temperature scale which can only ever be 0, hypothetically, and can never go through 0, like Celsius and Fahrenheit scales can. Another way to say this relationship is that V1 over T1 equals V2 over T2. The volume divided by the Kelvin temperature for a gas must always be constant. This is Charles' law. Similar to Boyle's law, V1 and T1 represent volume and temperature at one set of conditions, or for the original gas. V2 and T2 represent a new set of conditions for volume and temperature. So suppose that we'd like to know what temperature in degrees Celsius would be required to increase a balloon's volume from an initial value of 2 liters at 15 degrees Celsius to a final volume of 3 liters. Like in the previous examples, if we can come up with a list of variables, things that we know and things that we'd like to know, this can help us identify the appropriate equation to use to solve this gas problem. We know originally that our gas had a volume of 2 liters and a temperature of 15 degrees Celsius. So I know that V1 is 2 liters, T1 is 15 degrees Celsius. And because I'm dealing with a gas, anytime that I work with a gas, I'm going to immediately convert any Celsius measure of temperature into a Kelvin measure. To do that, I'm going to add 273. I'm going to do this straight away so that I don't forget to do it later. 273 plus 15 is 288 Kelvin. Next, I know that at a new set of conditions, the new volume is intended to be 3 liters. And we'd like to know T2. We'd like to know it in degrees Celsius. So we'll likely have one final step of extra work at the very end to get a Celsius measure of temperature. But for right now, because we're given volumes and temperatures at different sets of conditions, Charles' law looks like the most appropriate equation to use to solve this problem. V1, 2 liters, over T1 in Kelvin 288K is equal to V2, 3 liters, over T2, an unknown. And now we need to solve for a quantity in the denominator of the right-hand side. The easiest thing for us to do will be to multiply both sides by T2 so that we get rid of it entirely on the right-hand side. Now, on the left-hand side, there's a quantity that we can simply divide both sides by. If we divide both sides by this whole quantity, then 2 over 288 goes away on the left, and we'll be left with 3 liters divided by 2 liters divided by 288K. Eventually, we'll find that units of liters cancel, and we'll just be left with Kelvin temperature, like we'd expect for this problem. If we punch into our calculator 3 divided by 2 divided by 288, we end up with 432 Kelvin. Here, the temperature has increased from our initial value, and our volume has increased from 2 to 3 liters. According to Charles' law, we should anticipate an increase in temperature with an increase in volume. As volume went up, temperature went up. But we have one final step to do here. We were asked what the temperature in degrees Celsius needs to be in order to make this volume change happen. To get a temperature in degrees Celsius, we simply reverse this expression up above. A temperature in degrees Celsius is equal to a Kelvin temperature minus 273. Here, 432 minus 273 gives us 159 degrees C. This is our final answer. But notice that we could not use degrees Celsius up here and get the same result at the end. We need to use Kelvin temperatures in our Charles law and all other gas law calculations, converting from Celsius and or to Celsius as needed at the start or end of our calculations. Similar to Charles' law, Avogadro's law shows us that as the number of moles of gas particles increase, the volume of particles increase. Or, more simply put, the more stuff we have, the more space that stuff takes up. So, as the number of particles N increases, volume increases. Another way to put Avogadro's law is that V1 over N1 is equal to V2 over N2. This expression isn't quite as useful as either Boyle's law or Charles' law for our purposes. So I'll introduce the relationship between volume and number of moles here, but we probably won't use Avogadro's law in this form all that much. And lastly, Amonton's law, or previously as it was known, Gay-Lussac's law, shows us the relationship between pressure and Kelvin temperature. Here we see that as temperature goes up, the pressure of a confined gas goes up. Think about having a pressurized aerosol container. You always see a warning on those canisters that say do not expose to high temperature or open flame. The reason that you don't want to expose those things to high temperature or open flame is Amundsen's law. As the temperature of those gases inside a canister confined to the fixed volume increases, their pressure builds and builds until a canister can no longer hold them in. Another way to say Amundsen's law is that P1 over T1, again, where T is in Kelvin, is equal to P2 over T2. And like Avogadro's law, Amundsen's law in this form is not particularly applicable to us. But we have come up with a series of 4 laws that demonstrate the relationship between 4 quantities that measure gases: pressure, volume, temperature, and number of moles. Here are those equations again. Boyle's law. The relationship between pressure and volume for a gas is P1 V1 equals P2 V2. Charles' law. The relationship between volume and Kelvin temperature, V1 over T1 equals V2 over T2. Avogadro's law. The relationship between volume and number of moles. And Amundsen's law. The relationship between pressure and Kelvin temperature. At this point, with so many gas laws, you might be thinking to yourself that it might be useful to combine some of these into a single succinct law. And here, that's just what we'll do. And we'll give it a flashy name that's very creative in the vein of chemists. We'll call it the combined gas law. And we'll demonstrate what the relationship between pressure, volume, and temperature simultaneously are for a gas with a fixed quantity or number of moles of particles. This combined gas law is P1 V1 over T1 equals P2 V2 over T2. And this is a 5th equation that we can add to our arsenal. The combined gas law tells us how pressure, volume, and Kelvin temperature all relate to each other for a gas. So once more, temperatures must be in Kelvin, and Kelvin is a degree Celsius measure plus 273. It's not quite as direct to look at the combined gas law and predict what the effect on one variable will be given that we change 2 others. For example, suppose that we fill a weather balloon with 100 liters worth of helium, initially with a temperature of 20 degrees Celsius, and at a pressure of 755 torr. We'd like to calculate the new volume for this balloon. When it's reached some altitude, it really doesn't matter that it's 10 kilometers, so that's extraneous information. All we really care about is that at that altitude, the new temperature is negative 52 degrees Celsius, and the new pressure is 195 torr. In this example, we're going to write down, just like we did in the previous ones, a list of all the information that we're given and the quantity that we're trying to find. We're told that initially the pressure is 755 torr. That's a P1. And yes, this quantity is in torr, and I said we would use atmospheres for the most part in this chapter, but torr and atmospheres aren't an offset scale from each other. They're just a ratio scale. I can measure pressure absolutely in torr or in atmospheres, just as I can measure it relatively. And therefore, because I'm going to be comparing one pressure in torr to another pressure in torr, there's really no need for me to convert pressures, just as there's no need for me to convert volumes when dealing with these 5 gas laws. Really, the only quantity that we need to be concerned about converting units for will be temperature, and temperature should always be in Kelvin. So I'm going to leave my pressure in torr. You could convert it to atmospheres, but you'll get the same result as I will at the end of your calculation, and you can try it for yourself if you like. P1 is 755 torr. This corresponds to an initial volume, V1, of 100 liters, and an initial temperature, T1, whose units I will convert. 20 degrees Celsius, I'll immediately add 273, because this isn't already in Kelvin, to get 293 K. At a new set of conditions, the new pressure, P2, is 195 torr. The new volume is something I'd like to know. And the new temperature, T2, is negative 52 degrees Celsius. Once more, I'll convert it to Kelvin by adding 273, so that I come up with 221. Now, given this abundance of information, comparing pressure, volume, and temperature, we'll see that the combined gas law, P1V1 over T1, equals P2V2 over T2, is the most appropriate for solving this problem. To plug directly into the combined gas law, I'll take P1, 755 torr, multiply by V1, 100 liters, divide by T1 in Kelvin, 293 K. On the other side, P2, 195 torr, multiplied by V2, our unknown, divided by our T2, 221 K. To solve this equation, we'll multiply both sides by 221 K, similar to how we solved a problem earlier. When we do that, Kelvin on the right-hand side will go away entirely. We'll be left with just 195 times V2, and we can divide both sides by 195. So we'll put this quantity in the denominator on both sides. And when we do so, we'll solve for V2. V2 ends up being equal to 221 K times 755 torr times 100 liters divided by 293 K and 195 torr. Units of torr and units of Kelvin cancel. We're left with units of liters at the end. And if we punch this whole thing into a calculator, we end up with 292 to 3 significant digits, liters. Our new volume is expected to be 292 liters, a quantity that we might not necessarily have deduced just by inspection of this combined gas law relationship.